Lesson 6.4 is all about sine law. Up until this point, our whole unit has still been working with right triangles, looking at using the sine function, cosine function, tangent, but then also introducing secant, cosecant, and cotangent. Now we're going to take a step back, and instead of looking at right triangles, we're actually going to look at how trigonometry can be applied to non-right triangles. So this is new from anything you've learned last year. So we've got a couple different laws. We're going to start with sine law though. So that's today and the next lesson. So the first thing we need to note is that equations are only allowed to have one equal sign, which is why up until this point, if you have continued to write your work equals, 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 I have proceeded to write equals all the way down like this, because you cannot have more than one equal sign in a specific equation. That being said, the laws that we're going to look at are strictly written for the purpose of kind of summarizing the relationships. At no point will you actually use the entire law together. So the law itself for sine law says that for any triangle ABC, we can set up these ratios. So just to give you an idea, we're talking about any triangle at all, A, B, C. And remember that your opposite side is named with the same letter in lowercase, so A, B, C. So we can set it up as the ratio of the side length divided by sine of angle A. Could be set equal to either B, side length B, divided by sine of angle B, or any of these pairings could be set equal to side length C divided by sine of angle C. So that's option 1. Option 2 is we just flip it all over. As long as we flip every ratio, it's still going to be true. So both of those are totally fair game. So these are our laws and some key ideas that we need to know. When can you use sine law? Well, if you have two sides and an angle opposite a known side. Okay, so the key thing there is that it needs to be across from a known side. Another option is if you have two angles and any side. Now, why is this okay? Because right now, if we look at that second triangle, we don't know the angle across from it. And so we're not going to be able to plug in directly into our equation. But we do know that all the angles in a triangle add up to 180 degrees. And so if we can use that rule, I could take these two values, solve for my unknown angle. Now I do have a corresponding opposite side or opposite angle inside, and we're going to be able to do that. Okay, and so that's what this statement is saying here. When determining side lengths, it is more convenient to use this version of our law. Reason being, our side length is in the numerator. The second we have our variable in the numerator, just cross multiply and divide. That moving of numbers around becomes infinitely easier. So always put your variable in the numerator and then make your other ratios match. Okay, alternately, so side lengths, we want them on top. Angles, we want them on top. Okay, so going back to our description here, if you want to summarize it, we use this version for sides to find a side, and this version we're going to find angles. Technically, you don't need to switch it. You could work with just the left-hand version or the right-hand version. It's just going to be a couple more steps if you decide to do that when you're solving for whatever's in the denominator. So let's give it a shot. Example 1. In triangle GHJ, okay, and please note we try not to use I's because they look like ones. Determine the length of GH. So GH, I find that on my triangle. That's this side here. And so we could also call it J. So that's what I'm gonna kind of rename it. just for myself, and we're going to round it to the nearest tenth of a centimeter. Please be careful that you are doing exactly what the question asks in terms of rounding. So we go through and we say, okay, well, we're finding side J. Do we know the angle across from it? Check. We also have the pairing of G, angle G, with side G. And so we can set up our sine law. So it's always side compared to matching corresponding or opposite angle. So I'm going to put my variable in the numerator to make my life easier. So J divided by sine of angle J is going to be equal to side G divided by sine of angle G. From here we plug in and then we're going to need to isolate J. So we need to get rid of the denominator, sorry, and we're going to do that by multiplying. And we end up with J, and you're just going to plug this all in. So I get that J equals 6.972, but because my question asks specifically to the nearest tenth, that's only one decimal place, so I'm going to round it off after the 9. 7 rounds up, and so my final answer is actually going to be 7.0 centimeters. I put the 0 there so that I'm still accurate to the tenth. And then to fit our description in the question, I'll say it's equal to GH. And that's all it is. Example 2 is a little bit more complicated, but we'll do it together and we'll figure out how exactly it works. In triangle MNP, determine the measure of angle N to the nearest degree. So angle N is what we're looking for, to the nearest degree. And typically what we're going to be looking for is angles. We round to the nearest whole, and then side lengths, that can vary in terms of what we're going to round to. At least one decimal place is good though, usually. So the problem with angle N is that we don't know the side across from it, which means that we cannot use the ratio N over sine N, or vice versa, because we want our variable in numerator. So we wanted to be able to use this, but because we don't know that side length, we can't. Now you're like, Ms. Conrad, we could just use the Pythagorean theorem. But we can't, because the Pythagorean theorem is only for right triangles. So we can't use the Pythagorean theorem, which means we need to be able to use our sine law. But luckily, we can figure out P because we know its opposite side, and we do have one full complete ratio here of M. So what we're going to do is we'll solve for P. That will give us 2 angles, and then we know that all the angles add up to 180 in a triangle. So we'll take M and P, subtract those from 180, and those will give us our value for our angle N. So we're starting with M, and I'm going to put the angle in the numerator because that's what I'm still solving for. So sine M over M equals sine P over side length P. Plug and chug. Don't drop your units on your angles. That's just a reminder. Got sine of the angle I'm solving for over 10 centimeters. And again, we're going to multiply by 10, get it out of the denominator, and isolate sine P. Now at this point, it does become a little bit more complex than the previous question because we still have our function showing up over here. So what I'm going to do is I'm going to punch all of this in my calculator, and then I will take the sine inverse of that. So this whole setup of 10 times sine of 92 degrees divided by 11.8, that ends up giving me this value, this decimal. I'm going to keep as many decimal places as I can when I'm actually proceeding with my calculation, because I'm not done this question yet. So although I've written down just 5 here, I'm going to continue to work with all 10 decimal places that I have in my calculator. And how do we get rid of our sine function? We take the inverse of it. So instead of this, to kind of cancel it out or undo the sine function, we talk about sine inverse of 0.84694, etc., equals angle P. I'm going to punch that in. And I get 57.88 degrees. But again, we just need angles to the nearest degree, so we're going to round it off here. 8 rounds up, so I'm going to say that that is 58 degrees for P. Now that I know that angle P is 58 degrees, I can calculate N by going 180 minus M and P. And I get 30 degrees. Now this question could have asked us to go even one step further from here and solve for side N. And again, we would just use our sine law now that we know the angle of our N angle. We can solve for its opposite side using those sine ratios. And I would probably stick with using M again, just so that I'm using as few calculated values as possible, using as many of the givens, so that maybe if I made a mistake over here, I'm not going to keep carrying it through to all my other calculations. I'm going to try and minimize the damage if I did make an error. So you've got practice questions in your workbook. Go ahead and give them a shot.